I'll be talking about the operational performance and network integration of the wind farm. And I'll start with some general things that perhaps as the renewable generation is increasing, so is the importance of analyzing their impact on the grid. And particularly in the context of Scotland, and I would say also Spain, wind generation is an important or even the most significant renewable based generation resource. Difference between the PV and wind is that small and micro PV should be included into the analysis because, for example, there is around 6 gigawatts of micro and small PV in the UK, while impact from wind generation is predominantly coming from megawatt scale wind farm. Additional problem is higher mismatch between the generation patterns and demand patterns, as well as much higher level of stochasticity, variation, and unpredictability. All these uncertainties combined, and I was very happy to see that there are also uncertainty in the economic or non-technical part of the system. So I will just say very briefly here that we need good and accurate model of wind generation, particularly aggregate model, which are missing in the existing, let's say, knowledge database and literature. And I will talk about the most commonly known model for the wind generation, which is the power curve model. So let me try to illustrate the problem. What you see here is so-called manufacturer power curve, which is deterministic. So for any value of giving power output, it's obtained in control condition, while in reality we have something like that. So this is the actual field measurement for a single wind turbine in operation, while here we can see field measurement for a whole wind farm consisting of 6 wind turbines, 3 years of data. And I also have another from another wind farm, which is consisting of 14 wind turbines and 4 years of measurement. It is obvious that manufacturer power curve cannot be used for modeling the actual operational performance of wind turbines and wind farm as deterministic as opposed to the some kind of the probabilistic or distributional output of the actual wind turbines and wind farms. And also it will largely overestimate the production. What is shown with the, let me try to put the laser pointer, if I can. Okay. So what we also see here are so-called state-of-the-art model, DBScan and LOS, for assessing or processing the data in order to get what would be the operational performance. And we can see that they are not much different than the simple raw mean from all the scatter points, which are the different measurement points. There is also high uncertainty in the output. So I try to illustrate that here, we get very large output from this particular wind farm. And the reason why the model is not quite good, why we have this uncertainty, well, much of the thing happened is that the results here obviously have some outliers. So I would say it's clear that these are the outliers. If the wind speed is below cut-in, wind farm will not be able to produce output. And also, this data should not be used for the wind turbine analysis, because if the wind speed is high and power output is zero, something wrong happening with the wind turbine. And these are known, as I said here, the outliers which should be removed. And this is kind of chicken-egg problem, because in order to obtain the correct model of the wind farm or wind turbine, we need to remove the outliers, and we can have a clear idea what is the correct or physically valid, viable model of the wind farm. And these outliers are shown in the table and illustrated here. We can see, for example, there are different types of the outliers. Type A are low power out for high wind speed, so these are here. Then we have the difference when there is high wind speed, low wind speed and high power output, which are the D and C. And based on the effort in classifying or categorizing outliers, these are illustrated here, we may find out how to deal with them. That here is an algorithm that my PhD student carefully prepared in order to deal with outliers, and we can see how they're divided in different colored points or measurement points, which are then based on the particular category of the outliers. And after processing the data, we see here for 3 different to the same wind farm that some of these outliers are true outliers. So these outliers are false outliers, or they should be kept. They look like outliers, but they are not. And this is illustrated here in the table based on the different categories or type of the outliers. And an interesting point, because these are obtained in some kind of the statistically based or distance-based method. If we zoom in this part here, we see that we have some kind of the inconsistency. Some of these outliers, which are to be kept, are actually very interlinked or interlocked with the outliers which should be removed. And there is a very good question if green point here should stay and be used for the modeling and red point or red measurement should go. This way of statistical or distance-based of the outliers might be problematic because it's not physically or related to what we expect the wind turbine in this case, in this example, to be the behavior. And there is also this strange part here in which we see that a lot of outliers are being taken, or those who are false outliers and should be used for the analysis. And generally, this part around the cutout wind speed, so when the wind turbine is going from 1 per unit to 0 because of the protection, is also missing in the existing literature. In order to understand what's happening around the cutout wind speed, I'm showing here second by second measurement. So we have wind speed as the green, power output as the black. Here we see the point measured on the left side. These are second by second data. Then these are aggregated into the minute average value, and then at the bottom in 10-minute average value. And we actually see how the data which are being measured here from second by second or 1 hertz region are transferring in 1 minute. And then we got these points here, which are basically suggesting, I'll go back, why there are some area here which are around the cutout wind speed. Okay, we now know what's happening roughly there. So there is a question how to obtain a better way to find out the procedure for identifying and processing outliers. And based on this standard here, which is for operational performance of the wind turbine, we can assume normal distribution for the wind speed. We can take the actual measured standard deviation. We can then apply a large number of simulation, apply hysteresis control around the cutout wind speed, and then define boundary, which we obtain when we use manufacturer power curves model, so the one which is given by the manufacturer, to estimate what are the physically possible points, and we obtain something like that. So that means in our original measure data, we need to remove all these red points and some of the other outliers which are here, but keep this point, which is now giving us better way, because if you look here, there is no more overlapping between the adjacent points. This now opens the question, after we have these clear distinction and we know what points should be used for modeling the wind turbine performance, what would be the wind turbine model? And in terms of that, we develop a new 6-parameter power curve model, because you model around the cutout wind speed, which is represented here. So if we go from the outlier detection and classification to outlier processing and eliminate true outlier, but keep the false outlier, this is what we get from the measurement data. And this is between the model, which is being written here, and what would be the scatter plot based mean characteristic. I have to remind you that we started originally with that, and now we obtain something which is much better and analytically defined. So we have the operational model for the analysis of the wind turbine performance. If we talk about the wind farm level model, it's a bit more complicating because we have number of wind turbines which are operating, and there may be in 3 general states. So there may be total number A of the wind turbine in normal operation. Then there may be total number of B wind turbine which are operating but curtailed, and there may be total number C of the wind turbine which are not in normal operation, not curtailed. They're simply in some kind of the outage connection because there is a fault or there is maintenance or service. And if we now look at the wind farm with 6 wind turbines, we can find out how the previous clustering of the data is now explaining that in our operational model, we can find out based on the number of wind turbine indicated here, so all 6 in normal operation or 5 in normal, 1 curtailed and so on, we can find out what would be the output. An interesting thing is that for this wind farm, all 6 wind turbines are in operation only for around 1/3 of the total time. This means that the typical operating state of the wind farm is with not all wind turbines in operation. And another interesting thing here is if you look at the individual wind turbine for which output is 0, that means something is wrong when the wind speed is there, so the turbine is out, and this is an outlier. While when we look at the wind farm operation, when 1 or more wind turbines are out, as shown here, this is actually predominant operating region, and outliers at the wind turbine, individual wind turbine level is actually not an outlier if we are talking about the modeling the wind farm. Indeed, it will operate without all wind turbines in operation.
2 minutes left.
Yes, and I'm getting close, thank you. If we now fit our fully operational 6-parameter model, which is the blue line here, we can express any other state with any number in wind turbine out or in curtailed operation by scaling down or linearly combining that based on the number of wind turbine, which is allowing us now to represent this wind farm with particular operational power curve models. And again, this is what was the output of processing whole much better idea. When we look at the error or we want to validate, we find out that compared with all other methods with just discussed operational model, we got around a couple of percent error. More challenging, what happened here are that we have missing data, so the wind farm is not operating too much around the high wind speed area, which means that the imputation of a special type of missing data, so these are not missing data because they are not measured or recorded, these are missing data because they do not happen. It is very unlikely that we will have a lot of data here and allow us to develop the model. So therefore, we need to find a way to make the imputation of this data, which is a work in progress. And I'm finishing here with a more challenging problem, because if we do not have individual wind turbine measurement, as it was in previous case, so for another wind farm too, we can slightly redefine the model, and we can apply some kind of the fitting search in terms of the unknown number of the wind station and under the curtailment, when, for example, meta-heuristic or genetic algorithm could be used recursively, and then try to find out what is the likely number of the wind turbine within the wind farm in operation under curtailed or faulty, which is then giving us this model. And then the error here is maybe slightly higher, but still within a couple of percent when compared with the actual measured data, which again, I'm comparing with the original one, is giving a better output. So this is the last slide, is giving some of the references to follow that. And I will thanks for your attention and for any question or discussion. But last thing is I need to give special thanks and credit to Ming Zhu, my PhD student, who is actually behind a lot of these data and results that you have seen. So thank you, and I'm looking forward to your questions.